Hello everybody and welcome. In today's video we're just going to learn about ideal transmission lines and maybe see what kind of capable optimization techniques we can use to create a impedance matching network. So at the start we'll just go over transmission lines and ideal scenarios, and then later on in the CST schematic tool series we'll head over to microstrip because that's mainly what I work in. Okay, open CST schematic tool is just open up a plain CST environment, navigate over to schematic. There we go. Navigate over to block selection tree and click on ideal TL. Once you're here, we have a bunch of different blocks, and let's just go through and see what we can do with each single block. So here, transmission lines. So for example, we could get some sort of transmission line network here. Connect a port up to one end, and maybe we want to match a resistive load. So we put a resistive load at one end, change it to maybe 250, and we could create a third order system. Connect it all, G on the keyboard to get your ground, and we're just going to quickly make a S parameter task. Frequency range 1 or 0 to 10. Increase the fidelity to maybe 10,000 points. And what we're going to do is we're going to give impedance. So we're going to call it imp_1 and set it to be 50. For the second element, I'm going to change the impedance to be imp_2 and I set it as 50. And then I'm going to go imp_3 and set it to be 50 as well. I'm going to set the length of each individual one to be the same quarter wavelength because this is ideal transmission line. And if I want to make, like for example, a wideband quarter wavelength impedance matching circuit, each element, and you'll see this with filters, with coupled line filters, and most filters, you're going to find that the quarter wavelength is constant between every single piece of the network. Now the quarter wavelength may change once you get into microstrip because it's also width dependent. Okay, so quarter wavelength, and I'm going to set it to be maybe 5 to start off with, and I'm going to set the length QWL for all of them, and I'm also going to set them to have the same epsilon value. Let's choose 6.8, just a random value, and 6.8 for all of them. So I'm not going to set it to be a parameter because I'm not really changing the epsilon value. Okay, now I'm going to click onto S parameter and make sure it's not block dependent. I want constant 50. And then here I've got my third order network and I click update. I can check my S parameters and realize that it is completely mismatched over the full frequency range. So what I can do now is I can go over to tune, and I can start playing with the quarter wavelength or all the values. So I know I'm going to match a system and it's going to use quarter wavelength, and normally you'll see some sort of stepping nature. So the first one is going to be near 50. Let's say it jumps up. Let's go back to our schematic tool. If this is 50 and the end is 250, then it's going to be some sort of ladder. It's going to be 50, then maybe to 100. This one might be 150, and this one might be 250. And the last one, 250, or sorry, this one's 200. So you see that kind of ladder nature. And if you go back to some famous textbooks, either Poser or even further back, there's one called coupled line networks that's going to tell you exactly from in a wideband impedance matching network table, it will tell you what each impedance needs to be, and it will work perfectly every time. However, if you don't have access to that, or you just want to see what the impedance values do to the Smith chart or to your S11 response, now we can kind of just play around with the values. So I'm going to set a max value of 250 for every single one of them. And I'm going to set a value of 50 as the minimum for every single one of them. Okay, I'm going to click update. I'm going to go back to my S parameters, oh, we have a simulation error. Why is that? Unable to set up simulation task. Okay, let's just delete this task. I'm going to delete. Try one more time. Close the tuner. Update S parameters. 0 to 10. We'll see if that one wants to work. Okay, that one works just fine. Let's go back to tune. And we've got our old tuning parameters back. Okay, now I'm going to go through and I'm just going to set up that kind of, well, even with just a single value, we're starting to get quite a good match. So I'm just going to set up a single quarter wavelength impedance matching network just to show and just to leave there to show what happens when we have a third order system versus just a single element. So I know what the impedance is going to be. It's going to be similar to the last video, 50 times 250, close bracket, square root, 0.5. And the quarter wavelength is going to change, perfect. I'm going to click update. Yes, I would like to update it. And I didn't. See what happens when I don't state the block dependency. So constant because I closed the last one down. So constant, and update. Let's check everything. Perfect. So here's our perfect ideal scenario. And now we can go through and just play around with all the impedance values here and see if we can get a similar result. And you should find how difficult it is to start tuning without kind of a solid guess to get you started. So, you know, what impact does the second element have? And we can see that, oh, starting to get a worse match. So I'm just trying to get the red line as low as possible. So we can kind of see. Okay, we're not having too much luck. But even then, you know, your goal for impedance matching circuit, depending, -20 is very high performing, meaning only 1% of the power is being reflective. But you can see this perfect impedance match here is far better to what I'm attempting to tune, and so forth. Okay, and we can also try and tune from the Smith chart. So we can see how it perfectly went through the middle of the Smith chart, whilst our red one, oh, it's kind of twirling. I'm not too sure what's happening. Okay, and we can start to see, oh, so we're nearly getting a match condition actually here. So what happens if we bring the impedance of the third element? Well, look, we've got a match condition here. Let's go back to our dB. I've got a match condition at 1 gigahertz, but my quarter wavelength is still being designed for approximately 5.575. So that's a very funky kind of environment. We have some sort of low pass filtering network here. So this is kind of the benefit of using the Smith chart. So as long as one of the lines goes through this normalized impedance of 1, then you've actually got an impedance match. So you can start playing with all the values here. Oh, that's too much. Let's start seeing how the middle one impacts it. Oh, so we're seeing how we've got this interception point here. So if we could get this interception point actually near the 1, well, we're going to have a matching circuit that works quite well at 2 frequencies. So we've got it on the 1 here along this 0 kind of imaginary. There's no imaginary part to the crossover. We can see what that's looking like on the dB. Here are 2 frequencies that are achieving a match. And now we're going to see if we can play with the other parameters to try and drive that closer to 1. So we're getting there. So remember how it pulled it down using the impedance of the middle element. Well, now we can pull it, oh, very sensitive. So let's go for the min value of 90 and maybe the max value of 120. So we have some more kind of resolution to work with. And then I'm maybe 200 as our min value for the impedance of the first element. So I'm going to drive it a little higher. I'm trying to get that little crossover point, and I'm just going to tune back the impedance tune forward, sorry. So I'm overestimating, and I'm trying to drive it. Nearly there. Can I get it? I'm going to have to go over 250 actually. Let's go up to 300. Oh, nearly. I'm going to zoom in now. So this crossover point, I want to drive it to 1, which is located right here. And I should be close enough. So, you know, that's the benefit of using the Smith chart to match. You can kind of have a better understanding about where the Smith chart lines with respect to frequency. Because remember, you can go from this point here, which is your 10 gigahertz, and it's swirling all the way around back to where it's ending off at DC. So let's say if you want to only use a small section of frequency range, let's say I was matching at 5.75 gigahertz. You can go also to plot properties and change the auto range to maybe 4 to 6. In some scenarios, when you have the frequency range too large, you're going to get more of the swirling nature, and then it becomes very overwhelming trying to match via the Smith chart. So, but now because I've restricted the range, we can only see the point of 4 gigahertz swirling all the way up to 6 gigahertz. So if we wanted to, we can leave like a marker, but we can go back to the dB plot to see where it's kind of matched. So that's kind of the efforts of a third order network. And if you wanted to increase the bandwidth of this, you can either set the optimizer to go to work, and we can try that. We could say, well, maybe I want it to work over a new goal, so have control of all of my impedances. I'm going to let you control up to 50, and if you already have a good estimation of where your answers will lie, the better your simulation is going to be. But I know it's going to be somewhere between 50 and 250. And I'm not going to use trust region. I'm going to use CMA evolution strategy because it's very fast, and I know what frequency it's going to be working at. Use current value as anchors. Anchors, no thank you. Use data. Let's change. Let's actually drive all these values under a little bit so we don't have the error. Close tuner. Open the optimizer. And I just need to put in my values one more time. So 50, 250, 50. And I'm just clicking tab to do it a little faster. And 250. I'm still going to cause an error. I'm going to make this one 40. Okay. And now the optimizer is going to have a go at controlling these values under CMA evolution strategy. And I'm just going to go over to goals. And here's the most important. I'm going to state I want a magnitude lower than, let's say, 20 dB. Oops, sorry, I'm going to click edit again to access it. And I want it between a range of, let's say, I know the match frequency was 5.8 around there. So maybe 0.1. And then I'll copy this one to a max of +1. And I can click OK. And it's got the range 5.7 to 5.9. And I can then just click start and see what performance I can achieve. So info, I'm going to change the properties, just double check everything's okay. And if you wanted to, you can go general properties and state all for parametric result, meaning every single iteration it does, it's going to put that result into the result navigator. And that's a bit overwhelming because it's going to go very fast. And then you can click start. And then you can see it's doing heaps of simulations very fast. And you can see it's just trying out all different scenarios until it might be able to achieve it. And then if you don't supply it enough information, like for example, is there a possible solution? And yep, there we go. It's done the possible solution. So it was able to get 103, 157, and 160 impedance, achieved the following goal. And if I go down to my results, we can see here's the goal, here's the first attempt, and here's the best so far. So it seemed to nail that quite well. So now once we've given it some sort of an easy task, we can say, well, maybe, can you stretch the bandwidth even further? So I'm going to click OK. I'm going to state you can use data from previous examples. So it's going to copy and paste all 80 that's previously done before, and then see if you can change these values to improve it a little bit more. So start, click on S parameters, and it's done it very quickly. Let's increase the goal now. Edit. Let's do something a bit more courageous. Let's go for a gigahertz bandwidth and click start. There we go. It did it in three runs. And maybe this might not match what kind of result we wanted, but no, it did it perfectly. Okay. So we can see now we've actually achieved a wider bandwidth than the previous one. Even though it doesn't go to a single point, look at our usable bandwidth. We could even, like from here, this is pretty much a usable bandwidth. So let's go even further. Let's go -20, I'm happy with. I would like a 1 gigahertz either side. So 2 gigahertz bandwidth. Start. Perfect. There we go. And if I want it, let's say I want it even better. So there's going to be limitations, and when it struggles, like -30, let's click start. It will just get stuck in a loop and it won't be able to do any more. So it's going to see if it can test it, and you see some solutions are getting quite impressive. So we've got impedance value of 68 for impedance network, the number 1 network, and the number 2 was 131, and the number 3 was 216. And as I mentioned, for wideband networks, you can look up what these values are. There's some sort of stepping nature, to the impedance values. So trying to guess these by hand would be extremely hard. And let's go plot properties again. Let's go full range. We can see the difference between a wideband impedance matching Smith chart and just a single frequency quarter wavelength. So it has this sort of kind of bump. And you'll find with wideband systems on the Smith chart is they like to bunch up in the middle, where the loops on itself with like Chebyshev or maximally flat, you can see this sort of kind of flat nature and kind of like a love heart. Okay, so we can just continue to push the optimizer even further. But overall, I'm very happy with the performance I was able to get. And this is completely without even touching a textbook. So we've just asked the simulator to have a go at it. And if you then wanted to, you could take those impedance values that you've just calculated, and you could then spawn it in, for example, let's close this down, microstrip. So if you really wanted to, create the exact same with microstrip blocks. And then once you're happy with the microstrip block, you can then create it in 3D. So let's start having a look at another tool with ideal transmission line blocks. For example, a stub. So we can see what a stub is capable of. So ideal TL. We can drag a stub into this and we can connect it here. And then again, we're going to pass it just values we can control. So I'm going to call it stub impedance, set it to be 50, and then I'm going to set stub length. I'm going to set, if you're just trying to see what a component may do to your Smith chart or do to your system, it's always good to set it to be a very small value, and then you can start to increase it, because when it's very small, and if you're working at low frequencies, it's not going to have too much of an impact to the whole system, right? This is a fraction of a quarter wavelength, even at 10 gigahertz. So I've added a stub. I'm happy. I'm going to change the epsilon back to 6.8, same as everything else. And I'm just going to delete this port so I don't have the previous results. I'm going to click on S parameter task, and I'm happy with a constant value. And now I can change this to maybe 50 as well. And so quarter wavelength is the length I'm dealing with. Maybe I'll call that D length 5. And I click update. Yes. And now S parameters, here's my frequency range. I can check the Smith chart. It's terribly mismatched. But I can now just have a go at seeing, well, what does a stub do to a mismatched load? Or even if I had a match system, 50 to 50, click update, S parameters, right? this is looking like a very good match system. I can change my y-axis because it's right here. It doesn't offer too much. I actually want it to go back to 0. Max 0. There we go. So this is a very good, it's just a transmission line, 50 ohm in an ideal sense. And now I can also click on tune. And my two things to play with are stub, impedance, and length. So I can get a length value of maybe up to 10 and just start seeing what that does to my circuit. Oh. So at a length of 10, just a stub placed in line. So just a stub in line. If you really wanted to. Let's say it was a stub between two transmission lines. Update. Yes. We can just see what that stub is going to do. So we find that at 3 or around 3 gigahertz, we've actually got no energy or all the energy being reflected. So it's like a perfect stop filter. It's like, stop this frequency, I'm stopping it passing through. And if we really wanted to get rid of the load, let's just put another port. So now we can see kind of the filtering effect we get from just a single stub. So S parameters we find, remember this is a filter now. So that's our S11 and our S21. Okay, its pass band is over here near 6 gigahertz, and it also has a stop band right around here, just depending on where we're looking at. So you'll find that a stub will supply a perfect match or perfect pass through at certain frequencies, and then at another frequency will perfectly reject all the energy. So that's what you can do working with a stub. And if you wanted to, well, now you can go back to impedance matching capabilities. So you can kind of add your load here. And now you can kind of play around with, well, what happens if I have a 250 load? Click update again. And we can see that this is our S22. So the lower, the more matched it is. And then we can play around with what the values are going to do. So, oh, okay, that's a weird, funky effect. Oh, okay. And what does the impedance of the line do? Let's drive it to be something low. Let's go all the way down to 2 ohms. So we'll find that. Okay, now I've got 2 bands that are perfectly matched. Near 4 and one near 7. I can slowly tune that with a length, but you'll find it goes completely out of match when I change the length. So it's a bit tricky when you're working with impedance matching circuits, but we can also tune stuff from the Smith chart. So this is this kind of nature. If you can get this swirly nature all packed in very close to 1, then you're actually going to have a very wideband impedance matching network. But that's just the capability. So go around and test what a stub does, test what it does with a single transmission line, maybe see if you can control 2. And if you'd like to see how to use the schematic tool to do impedance matching, I've done a previous video in my beginner series. I think it's one of the later videos, either around 6 or 9, where I go through techniques to achieving a stub matching or stub matching from scratch with the CST schematic tool and using the admittance Smith chart. So that was just my introduction to ideal transmission lines, and in the next video we'll dive deep into microstrip transmission lines. Thank you for watching.